Hello and welcome everyone. In this video, I will be discussing about the symmetry elements that are present in a tetrahedra. So before explaining the symmetry elements which I have given in the table, I will be representing the tetrahedral polyhedra. I have represented 4 different structures there. How to visualize them I will show. Supposing that if this is a polyhedral structure, okay, the first one is this representation where one of the triangular faces is towards you. 1, 2 and 3, this is one triangular face that is pointing towards you, one vertex is away from you, and this is to be represented in the manner that I have given you. Okay, that corner is away, or regularly we draw tetrahedra in this manner where one of the corners of the basal triangular face is pointing towards you. So this is pointing towards you. For that reason the below representation has been given. The below representation is this, above representation is this. For the next 2 structures, well, this is the representation for the next 2. One is above, the remaining 3 are facing below. Another important representation where you can understand the alternating axis or the SN axis is to hold the molecule in this manner. Instead of holding it this way, you try to hold it in this way. Once you are trying to hold it in this manner, you can check these 2 are vertical with respect to you, these 2 are horizontal with respect to you. Always there should be some alternate, always there should be some reference. That reference point is you. With respect to you, this is vertical, with respect to you, this is horizontal. Okay, so this is the the third representation above, and this is the 4th representation below. Now let's understand the symmetry elements. To get these symmetry elements, for convenience, what I have done is to understand the symmetry elements of molecules with special symmetry, especially tetrahedra, octahedra or icosahedra, you try to pass the symmetry elements starting from the corners, then let's move towards the faces, and finally let's move towards the edges. If I choose the corners, try to pass all the symmetry elements through the corners, check for every symmetry element, then move towards the faces, check for every symmetry element, move towards the edges, check for every symmetry element. If you can follow this convention, you can deliver all the symmetry elements very easily. For tetrahedral point group TD, altogether there are 24 symmetry elements. Uppercase T, lowercase d, and d must be a subscript. Out of the 24 symmetry elements, identity is always present. There are 8 C3s and 3 C2s, 6 S4s and 6 sigma d. Now let's understand these symmetry elements. Identity is always there, forget about it, because it's the identity of that particular molecule, it is always there. Later on, coming to the corners, if I start with the corners, the opposite is your face. The opposite of every corner is a triangular face in the tetrahedra, right? So if I am choosing one pair, this is a pair of a corner and opposite triangular face. There are 4 such pairs. Okay, listen very carefully, you will very easily understand. For a corner or a vertex, opposite is a triangular face. There are 4 such pairs. For one vertex, one face, second vertex, second face, third vertex, third face, fourth vertex, fourth face. From every pair of a corner and an opposite triangular face, a C3 can be passed. Once I pass a C3, rotate by 120 degree angle, it will give you an equivalent configuration. Okay, rotate by another 120, equivalent. Rotate by third 120, that will give you identical structure. If I am able to pass a C3 from a pair of a corner and one triangular face, I can also pass another C3 from second pair, third C3 from third pair, and fourth C3 from the fourth pair. Each C3 is passing from a pair of a corner and an opposite triangular face. So if I am choosing the vertices or the face, because opposite of a vertex is a face, opposite of a face is a vertex. Which axis of symmetry is present through the vertex or a face? C3 is present. How many number of C3s are there? 4 C3s are possible, because from each pair a C3 can be passed. Since there are 4 pairs, 4 C3s are possible. From the generation of symmetry elements, C3 will generate 2 elements, C31, C32. C33 is anyway identity. Identity we have already written, any repeated element should not be written. So each C3 will generate C31, C32. There are 4 C3s, each of which will generate 4 C31 and 4 C32. The total is 8 C3. We have completed 8 C3. Corners are completed, faces are completed. Now we are just left out with the edges. For every edge, opposite is also an edge. I will show you in a different model. Now suppose if this is the tetrahedra, okay. Within this tetrahedra, if you can see the red one which is pointing towards you, away is another red. They are perpendicular to one another, but that is forming one pair. For green is green, for orange is orange. You can check. And for orange is another orange. So if I am just trying to choose one of these pairs, from each pair a C2 can be passed. So from here, if I rotate by 120, not 120, if I rotate by 180, that will give you an equivalent configuration. Okay. So from each pair of the opposite edges, one C2 can be passed. From orange, one C2 can be passed, and from red also one C2 can be passed. Rotate by 180, it will give you an equivalent configuration. There are 6 edges in 3 pairs. From each pair of edge, one C2 will be passing. So altogether we have 3 C2s. Okay. I am just repeating this point. There is another axis of symmetry other than C3, that is C2, and each C2 is passing from a pair of edge. Altogether there are 3 pairs of edges. Therefore 3 C2s are possible. Each C2 will generate only one element, C2 1. C2 2 is anyway identity. So it is giving you 3 C2s. We have completed C2s also. Collinear to this C2 is S4. S4 is collinear to C2. So Sn axis of symmetry, which Sn axis of symmetry is present? S4 is present. How many S4s are there? Altogether 3 S4s. Why there are 3 S4s? Because S4 is collinear to C2. When there are 3 C2s that are possible, 3 S4s will be present. Each S4 will generate 3 elements. S4 1, 3, S4 3, 3 number. 3 plus 3 is 6. So altogether there are 6 S4s. How to visualize these S4s? Now I will just represent. Supposing that I am holding the tetrahedra in this manner. From here will be a C2. Collinear to this C2 will be S4. S4 means, you carefully look at this orange color one which is vertical with respect to you. I just rotate by 90 degree. When I have rotated by 90 degree, it is not an equivalent configuration, but forget about it. It is S4. S4 means you have to rotate and then reflect, then you can get an equivalent structure. It is improper axis. Sn is an improper axis in tetrahedra. I have rotated and then followed by a perpendicular reflection. So once I pass a plane perpendicular to rotation, the away half will reflect towards you. It means this particular half is reflecting towards you. I am repeating it again. This is the orange one which is vertical towards you. Rotate, not an equivalent configuration. Reflect, the away half will reflect towards you, and it is giving an equivalent configuration. So if I am able to pass an S4 from orange pair, I can also pass an S4 from a red pair, I can also pass from a green pair. Wherever a C2 is passing, there S4 can also be passed. Therefore we say S4 is collinear to C2. Since there are 3 C2s possible, 3 S4s are also possible. Each S4 is generating 3 elements. Altogether 6 S4s are present. S4 is also completed. The last one, now suppose if I hold it in this manner, you just look, from the greens is one C2, okay, from the orange is another C2, From the red is one more C2. If I can consider this C2 and this C2, these two C2s, they are making some angle. That angle we call it as a dihedral angle. Dihedral angle is an angle subtended between two similar consecutive C2s. And any plane that bisects this dihedral angle is called as a dihedral plane. So when I am holding it in this way, if this is one C2, this is a second C2, a plane which bisects is called as a dihedral plane. So it is bisecting that angle subtended between the two C2s. It means each dihedral plane is passing through one of the edges completely, and it will come out from the center of the opposite edge. You can check. Okay. So if you are just trying to pass an imaginary plane, that plane is taking up one edge completely and it will come out from the center of the opposite edge. How many edges are there altogether? 6 edges. So from each edge one plane will pass. And since it is bisecting the dihedral angle, you can call it as a dihedral plane. Since there are 6 edges, 6 planes are present. All these planes are taken as dihedral planes. Plane of symmetry, dihedral plane is present. How many number? Altogether 6 sigma d, and 1 sigma d means it is just 1 sigma d. It will not generate many symmetry elements. Therefore, altogether 6 sigma d. We have completed it, right? So just let me conclude. For tetrahedra, altogether there are 24 symmetry elements: E, 8C3, 3C2, 6S4 and 6 sigma d. To pass these symmetry elements, you have to check for the vertices, corners and the edges. In tetrahedra, for any vertex, the opposite is a triangular face. So altogether there are 4 such pairs. Each pair has a vertex and a opposite triangular face. From each pair of a corner and opposite triangular face, one C3 is possible. Since there are 4 such pairs, 4 C3s are possible. Each C3 will generate 2 symmetry elements, and hence altogether there are 8 C3s. This is a molecule that comes under molecule with special symmetry, where there is multiple higher order rotational axis. For lower molecules, you can see that there is only one higher order rotational axis, but for this you can find altogether there are 4 higher order rotational axis, 4 C3s, each of which is generating 2 symmetry elements. Once the corner and the opposite triangular face is completed, let us come to the edges. There are 6 edges in a tetrahedra falling in 3 pairs. From each pair of the opposite edges, one C2 will pass. Since there are 3 such pairs, 3 C2s will pass. Each C2 will generate only one symmetry element, and hence we have 3 C2s. Collinear to C2 is S4. So from wherever we are trying to pass a C2, from there you try to pass a S4. One logic I will tell you here: for an edge, if there is an opposite edge which is staggered to it, they are perpendicular to one another. So if there is a Cn, there will be S2n present. That Cn is a C2. Then S2n will become S4. For C2, S4. Suppose if there are 2 edges that are staggered, and if there is a C3 possible, there will be S6, C4, S8, C5, S10. That will continue depending upon their staggered nature. For tetrahedra, for these 2 edges, C2 is present, and hence S4 will be possible. Altogether, how many C2s are there? Means 3 C2s. Therefore, 3 S4s are possible. Each S4 will generate 2 symmetry elements, S41, S43, and hence altogether 6 S4s are present. Corners are completed, faces are also completed. Let us come to the edges again. Through the edges we have seen C2 as well as S4. Also every plane is present, each plane will be bisecting one of the edges. Since there are 6 edges altogether, each edge is taking one plane, and hence 6 planes are present. Each of this plane can be identified as a dihedral plane because it is bisecting the dihedral angle made by 2 similar consecutive C2s. So we conclude that there are 6 dihedral planes. These are the 24 symmetry elements of tetrahedra. Remember an important point: there is no inversion in tetrahedra. This was one of the previous exam questions. For which of the below polyhedra there is no inversion? So you have to remember it as tetrahedra. Tetrahedra has no inversion in it. When I go for octahedra or cube, we can generate an inversion, that I will show how to generate. But this is the symmetry elements for tetrahedra. Thank you.